I've been designing a seismometer to be used for subsurface and surface level ice movement detection. Europa Clipper has launched, but Europa Clipper won't land on Europa, so this will be for a future landing mission. Okay, in my midterm video I went over the physics behind the seismometer, so this time I'll go over some of my design choices. So a seismometer is highly sensitive, precise, has a wider frequency response compared to alternatives such as geophones, large range detection. Here's a schematic that I used last time as well. I went with an Arduino Uno R3 for my microcontroller. It's simple to use, affordable, can connect to other devices over the I2C circuit, has open source code and real-time prototyping. Here's an image. And the sensor I use is the MPU 6500, which has both an accelerometer and gyroscope. It's highly sensitive, consumes low power, has a DMP which speeds up processing, as well as an I2C bus. Okay, so my design has been modified slightly since the midterm video. The hardware is still an Uno R3 and wiring and the accelerometer. But now I have 3 alert LEDs, red, green, and blue, as well as 330 ohm resistors that were calculated to provide the necessary resistance for the LEDs. As well, a level and rubber feet have been added to the design. So here you can see these additions. The software has largely remained unchanged, but more emphasis has been placed on the use of MATLAB and its toolboxes. Here's a schematic of the design, all the parts fit together. And finally, the entire prototype as an image. There are places for tapping and testing. Okay, so just a little bit about the results of my testing, specifically with the focus on the fast Fourier transform within MATLAB. Here's the acceleration graph, outputting the accelerometer values in X, Y, and Z. I'm giving it a gentle push in the Z direction, so the alert LED is letting the user know there's a significant change there. Just a bit about the FFT. It's been improved since the midterm, bugs have been fixed. It's now outputting the discrete Fourier transform properly, as well all the low-pass filters have been activated for the accelerometer gyroscope. So here we go, this is the results of the FFT. As you can see, there's dominant frequency slightly greater than 250 Hz for both the Y and Z axis, and then a very low dominant frequency for the X axis, as we expected. So this is just a clear example of the FFT from a previous test. You can see there's a very significant peak at around 130 Hz for this test case, and this would correspond to the frequency at which the tap occurred. Please see my report for more details. So the other major addition is the spectrogram. Here I've activated the other graphs, including the angular velocity graph. The spectrogram on the bottom right. Essentially, it's taking a short time Fourier transform by taking small windows of the time series and plotting it in a colorful way as a function of time. It's taking in live data from the accelerometer, so there's a bit of lag due to the computational resources required for all these graphs to work, but this has been the other addition. Okay, so just some future development next steps if the seismometer can be improved. Additional sensors could be added. For example, the position of a seismic event could be triangulated with additional sensors. A high-pass filter was something I would have liked to work on, but it was not in a finished state, so that would be great to block out anything below the cutoff frequency. The sensors themselves could be calibrated further, especially within MATLAB, and as well the spectrogram, just in the previous slide, could be made more accurate. Thank you very much for watching and listening. Please see my report for further details, and feel free to reach out if you have any questions.